In this lesson, we're going to be looking at Avogadros Law and molar volume. So let's talk about first the relationship between moles of a gas and its volume. And this relationship is known as Avogadros Law. And so if you consider this, when temperature and pressure are kept constant, if there's an increase in the number of moles of a gas, it's going to lead to an increase in the volume. Right, which hopefully just makes sense, right? You put more gas into something, temperature and pressure has to remain constant, therefore the volume is going to have to increase. There's going to have to be more space for the extra gas. So the volume of a gas is directly proportional to the amount of that gas. So mathematically that can be expressed as VI over NI is equal to VF over NF. And we probably won't use that particular equation at all. But we will be using this idea of the relationship between moles and volume. So as part of Avogadro's law, he hypothesized that if you have equal volumes of any ideal gas at the same temperature and pressure, it will have the same number of molecules, regardless of the chemical nature and physical properties of the gas, which means regardless of what it is, equal volumes will have equal number of molecules. Right? So another way to say this would be 1 mole of a gas occupies the same volume as 1 mole of another gas at the same temperature and pressure. So at a consistent temperature and pressure, if you have 1 mole of carbon dioxide, or you have 1 mole of helium, or you have 1 mole of propane, or any gas, it will all take up the same space. It doesn't matter what it is. And so this idea brings us to molar volume. So the molar volume of a gas is the space that is occupied by 1 mole of the gas. So molar volume is equal to the volume divided by the number of moles. And the units for molar volume are liters per mole. So before we do some calculations involving molar volume, we need to talk about standard temperatures and pressures and what that means. So recall that standard atmospheric pressure at 0 degrees Celsius was 1 atmosphere, or converted into different units, so 101.3 kilopascals or 760 millimeters mercury or torr. So that was standard atmospheric pressure at 0 degrees Celsius. And that 0 degrees Celsius, which is the freezing point of water, and is also 273 Kelvin, is defined as standard temperature. So together, those conditions are referred to as standard temperature and pressure, or STP. So whenever you see that acronym STP in a question, you know you're dealing with 1 atmosphere and 273 Kelvin. There are another set of standard temperatures and pressures, which are called standard ambient temperature and pressure, or SATP, and these are closer to the normal conditions under which we live. So these conditions are defined as 25 degrees Celsius, or 298 Kelvin, and 100 kilopascals. So in a question, when you see SATP, those are the conditions that it's referring to. So let's go through a sample problem about how we can calculate molar volume. So here's our problem. We have a resealable 1.30 liter container, and the container itself has a mass of 4.730 grams. Nitrogen gas is added to the container until the pressure is 98 kilopascals at 22 degrees Celsius. Under those conditions, the container and the gas have a mass of 6.185 grams. Now, the question wants you to calculate the molar volume of nitrogen gas at STP, so at a different set of conditions. So there's a lot of information given in that question. So first of all, the initial volume of this gas is 1.30 liters. The initial pressure is 98 kilopascals, and the initial temperature is 22 degrees Celsius. We want to find the final volume, right? We need to calculate a molar volume, which means we need a volume at STP. Our final pressure is our standard pressure, 101.3 kilopascals, and our final temperature is 0 degrees Celsius. Some other information we're given in this question is the mass of the container, 4.730 grams, and the mass of nitrogen plus the container, 6.185 grams. So there's all the information that we're given. We know we're going to need to convert those temperatures to Kelvin, so we'll do that. So we've got 295 Kelvin as our initial temperature and 273 as our final temperature. So the question is asking for the molar volume of nitrogen gas at STP. So molar volume, we've just talked about, is equal to a volume divided by a mole. So we're going to need those two things, a volume at STP and the number of moles, which is not going to change when the temperature and the pressure changes. Okay, so to calculate the molar volume, we'll need the number of moles, which we can find because we have the mass, and we're also going to need the volume, which we can find with the combined gas law. So first, let's find the number of moles. So we need the mass of just the nitrogen, and we can find that by subtracting the mass of the nitrogen in the container, subtracting off the mass of just the container. So we get 1.455 grams of nitrogen gas, and then we're going to convert that to moles using the molar mass of N2. And we find that in this scenario, we have 0.051927 moles of nitrogen gas. And so notice that I'm not rounding that too much because we are not finished the question. So I'm going to take some extra decimal places into the next steps of the question. Okay, so now we've found moles. So our next step is to find the volume at STP. So we're going to use the combined gas law to do that. So we're going to plug in all the values that we have with our VF as an unknown, and then we're going to isolate VF by cross multiplying the 273 across to the other side, and then bringing the 101.3 down into the denominator on the other side. So we get that VF is 98 kilopascals times 1.3 liters times 273 Kelvin, divided by 295 Kelvin, and divided by 101.3 kilopascals. If we look at the units, the kilopascals are on the top and the bottom, they're going to cancel. The Kelvin are in the top and the bottom, they're going to cancel, leaving us with liters, which is a unit for volume. So when you put all those numbers into your calculator, you get that the final volume is 1.16386 liters. Again, carrying some extra decimal places. So now we have the moles and we have the volume, so we now need to calculate the molar volume. So molar volume is a volume over the number of moles that occupy that volume. So these are the numbers we've determined in the question, 1.16386 liters over 0.051927 moles. So we get an answer of 22.4 liters per mole. So this is the molar volume of nitrogen gas at STP, but it's also the molar volume of any gas at STP, right, according to Avogadros Law. So no matter what gas you're talking about, if your conditions are STP, you know that 1 mole of that gas is going to take up 22.4 liters. So you can use that value in a question whenever you have STP conditions. If you have any other conditions, that number is going to change. For SATP, the number is 24.8 liters per mole. So whenever you have SATP conditions in a question, you can use the value 24.8 liters per mole. Okay, and those numbers will be provided to you for any assessments. So now let's talk about how we can use molar volume, particularly when we have STP and SATP conditions. So suppose you've got 15 liters of methane gas at STP. You could answer a variety of questions here. You could figure out how many moles are present. You could figure out what is the mass of the gas, and you could figure out how many molecules of gas are present. So let's do those individually. So first of all, A, how many moles are present? So we just talked about how the molar volume at STP is 22.4 liters per mole. So we're going to use that as a conversion factor to convert from that volume to moles. Or you could also just use that equation, molar volume equals volume over moles, and solve for moles. So if we use it as a conversion factor, we take the volume, and we know that 22.4 liters is equal to 1 mole. So we set up our conversion factor, and we find that we have 0.66964 moles in that 15 liters of methane gas. And to the correct number of significant figures is 0.670 moles. And so this would apply to any gas, remember. So it says there's methane, but in terms of moles, if you had 15 liters of any gas, there would be 0.670 moles at STP. B asks what's the mass of the gas, and here is when it matters that it's methane, because methane has a specific molar mass. So we take the moles that we calculated in A, the non-rounded answer, and we're going to convert that to mass using the molar mass of CH4, which you can calculate to be 16.05 grams. When you multiply those together, you find that there are 10.7 grams of methane gas in 15 liters. And then finally, you could also convert from moles to molecules using Avogadro's number. If we have that many moles, we know that there are 6.02 times 10 to the 23 molecules in every mole. So we have 4.03 times 10 to the 23 molecules in this 15 liters of methane gas. Okay, so B and C are calculations that you've done before. We've now just added in this idea of a molar volume, which can apply to any gas, but is dependent on the conditions, right? So standard temperature and pressure, it's 22.4 liters per mole. Standard ambient temperature and pressure, it's 24.8 liters per mole. But if it's any other temperature and pressure, that number is going to change.